I want to go back to a statement that we made in the last video. We made two important statements. The first was that we can only compute probabilities of events. The second is that events are subsets of the sample space. And so from those two statements, we realize something, which is that we're basically talking about probabilities of sets. And as a consequence, in order to do anything meaningful in probability, we have to understand a little bit about set theory. That's very much going to come into play here. So let's go ahead and first of all kind of develop some basic notions and talk about some things that you probably already know from set theory. So the first thing we're going to do is we're going to talk about this thing called the universe. And the universe is a vague term, but it's basically the collection of all the objects that we're interested in. Normally in probability theory, it's usually all the outcomes from an experiment or the sample space. And of course, a set is any collection of objects from those universe, okay? And so, for example, if you're talking about the magnitude of an earthquake, all right, the universe is all the real numbers, and the sample space is some subset from 0 to 10, okay? The main thing about sets that's important is we're only interested in membership. We want to know if a particular element from the universe belongs to a set, if it's in the set, in that collection. And so we use this symbol, this thing that looks like an epsilon. And what it means is that some element X from the universe is an element of the set A. Okay. One thing about sets that's important is to realize that duplications do not count. Okay. So the set consisting of 1, 1 is the same as a set consisting of 1. We don't count elements twice. We're only interested in if they're in the set, period. For notation, we usually put a curly bracket around the elements of a set, and we have different ways that we can denote sets. First, we can explicitly list the elements. So if A was a set 2, 4, 6, and there, in this case we don't have a lot of elements, we could just write out the elements in the set. Sometimes if it's implied and the person can recognize the sequence, we don't have to list all the elements. Let's say if it's infinite or there's a lot of elements. So for example, if we look at the set of even numbers, I can just write B is equal to the set 2, 4, 6, dot, dot, dot. And it's implied that I mean all the even numbers, okay? Even natural numbers, I should say. Now, sometimes we use a more sophisticated way, this thing called set builder notation, where we basically say the condition required for membership in a given set. So if I go back to the set B, I could say, instead of just saying it's some sort of implied list, I could say B is the set of all n that are in the natural number such that n can be written as a multiple of some other natural number. Okay, that's set builder notation, and it's very commonly used. Now we're interested in subsets, right? Because that's where the events are. And a subset is basically a part of a set. So if I have any two sets A and B, the condition that A is a subset of B is that every element of A has to be in B. In other words, the set B in a sense contains all the elements in the set A. And we denote this by this sideways U. One way you can think of it is some people think of it as a less than sign. Okay, if you're inside of a set, you're less than the set you're inside of. Finally, we have to come to the notion of set equality. What does it mean for two sets to be equal? Well, what it means is that one set has to be contained in the other, and the other has to be contained in the one. So if I have two sets A and B, I'm going to say A is equal to B if and only if A is a subset of B and B is a subset of A. And it's important to understand this is how we prove two sets are equal. We have to show this right hand side, that each is a subset of the other. Okay? Now, If we were only dealing with individual sets, it would be very, very boring. Okay, we need to do a little bit more than that. We need to find ways to combine these subsets to make more complicated sets. And this is the notion of a compound event. So what are the different things that we can do to sets to make new sets from them? Well, the first thing we can do is we can do this thing called, and this is basically what I've just said. Okay, we're just building up more complicated ones. But before I get to the actual ways we can do this, I want to show you one thing though, which is called a Venn diagram. You're probably familiar with it. And it's basically just a way of pictorially representing sets. So let's suppose I look at the set of a sample space from the roll of one die. Okay, and I have two events. The first is the event that I roll a 2, 4, or 6. That's A. And B is the event that I roll a 3 or a 6. And the point is that I can represent these by drawing this box, which is the sample space. Notice that all the numbers from 1 to 6 are inside of there. And I can represent the sets A and B within that box. Okay, so the events are subsets of the sample space. You see that they lie inside the sample space. Okay, now we want to get a feel for what we can do with these events to make more complicated events. And the first thing we can do is we can take the complement of an event. So the complement of E is everything that's in S but not in E. Let's look at the Venn diagram for that. So notice that if I have some event E, just a subset, right, of the sample space, notice that it basically partitions the sample space into two parts. The set E and all the guys that aren't in E, and that's the complement. So mathematically we'd write the complement as all the elements of S such that they are not in E. Okay. Two useful facts about the complement. The first is that if I take the complement of E complement, I get E back. Okay, and that makes sense. If you think, look at this diagram. What are all the elements that aren't in E complement? That's E. Therefore, E is the complement of E complement. Okay, you can see that very, very nicely. The other fact, and this is a little more subtle, when we're doing proofs involving complements, it is very useful to say that it's the negation of the statement that X is an element of E. Okay, that's a very useful thing. Now, there is a concept that's related to a complement, and that's the set difference. And so when we talk about A minus B, what we're doing basically is we're subtracting off all the elements of A that are also in B. Or another way of saying this is that it is all the elements of A that are not in B. Let's look at an example, okay? And so this difference is basically subtracting off the part of B that's in A, okay? Let's look at a picture. Suppose we have the same sample space we had before, and I want to ask the question, what is A minus B? What is the set of elements that are in A but not in B? Well, notice that's 2 and 4, right? And so that's going to be the set difference of A and B. Okay. What else can we do with sets? Well, we can take unions. Sometimes it's called a conjunction. And so here's how that works. We're going to say that A union B, that's what that notation means, is the set of all elements in the sample space that are in A or in B. Now it's very important to realize that this OR is what we call an inclusive OR. Okay, let me show you what that means. So let's go back and look at our example, okay, that we had before. So A union B, what the inclusive OR means, it's all the elements that are in A, which is 2 and 4, or B, which is 3, or both, which is 6. Okay? There is a non-exclusive or. That's the NOR statement in logic or computer science, right? It means A or B, but not both. But that's not the or that we're talking about, okay? Now, we can kind of generalize this a little bit. We can turn this up. We can talk about a collection of sets. Instead of 2 sets now, we can have basically a countably infinite number of sets, right? And we can talk about their union. Okay. So E is basically the set of elements that is in one of these ANs, right? So that's kind of a useful thing that we're going to use a lot. Countable collections of sets. What else can we do with sets? Well, we can not only look at what happens when we add them in a sense, but we can also look at what happens when we take their intersections. And we look at the things that are in both sets. Okay? And so we have A intersection B with this little upside down U as a symbol. And so this is just basically the set of all elements in S that are both in A and B. Okay, it's where the 2 sets overlap. So if we look at this Venn diagram with our same example, what is the intersection of A and B? Well, it's where the 2 sets overlap, right? It's all the elements they have in common. And of course, that's just the element 6. Okay. Now again, we can take intersections of families of sets, okay? So again, I can have a countable number of sets, a countable collection of sets, and I can take their intersection. That should mean intersection, not union. Sorry, I'll change that. So notice that this is the set of all elements that are in A1 and A2 and A3 and A4. In other words, they're in all of the ANs, right? Okay. Now, we can look at intersections and unions together, and there's 2 important facts to know mathematically. The first is that they each distribute over the other. Okay, so first of all, an intersection distributes over a union. Okay, so it's kind of important to understand this. You could think about this as multiplication and addition, okay, in a sense. And unions distribute over intersections. Okay, you can prove this mathematically, by the way. We're not going to. It's a little tedious to prove, but you can in fact prove that. Now, there's one other thing that's kind of nice to know, which is that intersections are commutative and associative. What does commutative mean? Well, it means that the order in which we take 2 intersections doesn't matter, right? And of course that makes sense, right? I mean, just thinking about definition of intersection. It's also associative. It means that when we have 3 intersections, it doesn't matter how we group the intersections. We can perform them in any order, okay? And the same is true for unions. They're also commutative and they're also associative, okay? Okay, there's one thing that's actually very important, and this is called De Morgan's law. And this is a relationship about unions and intersections and complements. And what it says is the following. It says that for any 2 sets A and B, if I take the complement of their union, it's the intersection of their complements. And there's a second statement that says if I take the complement of an intersection of 2 sets, it's the union of their complements. Notice what happens in both cases. When the complement in a sense distributes, it turns a union to an intersection, or an intersection to a union, and it takes the sets to their complements. Okay? This is such an important theorem that I want to prove this. So I'm going to prove the first statement. So let's go ahead and let's suppose that X is an element. And what do I have to do to show these 2 sets are equal? I have to show that if I'm in here, I'm in here, and if I'm in here, I'm in here, right? If and only if. And I'm going to prove them both at the same time by using an if and only if statement. So I'm going to say, okay, X is an element of the complement of a union if and only if it is not the case that X is in the union, right? And now if I use the definition of union, that's true if and only if X, it is not the case that X is in A or X is in B. And now I'm going to bring this negation across an OR statement. And when I bring a negation across an OR statement, what happens? Well, it turns the OR to an AND, and it negates both of the statements, right? So now this is true if and only if X is not an element of A and X is not an element of B. Well, if X is not an element of A, where is it? It's in A complement, right? So now I have that this is true if and only if X is in A complement and X is in B complement, and if X is in one set and another, it's in the intersection, right? If and only if X is in A complement, intersection B complement. This is the end of the proof. Now I want to prove the second statement. It's actually very easy, because notice what I can do is I can take the first identity, and instead of using A, I can use A complement in its place, because it's true for any sets. So if it's true for A, well, A complement is just another set, right? So let's start off doing that. Notice I have a complement of a complement, which is going to yield the original set, right? Okay, and now I'm going to take the complement of both sides. Okay, and notice now I'm done. Okay, that's the end of the proof. So it actually becomes very easy to do. The last thing I want to talk about is the null set. The null set is represented by this what it looks like an O or a 0 with a slash through it. It's read the null set of the empty set. Empty set's probably a little better term to use, because null set means something else in mathematics, but I'm going to use null set, okay? Because we're not using it in that other sense, so there won't be any ambiguity. And basically it's the set that contains no elements. If you wanted to define it mathematically, you could say it's a set such that X is an element of the null set and X is not an element of the null set. Well, that's a contradiction. You can't be in a set and not in a set, therefore that has to be the set that contains no elements. Here's some very useful things to know about null sets. The first is that it's a subset of every set. Very important. Okay. The second is that the complement of the sample space is the null space. Okay. It follows from that the complement of the null set is the sample space. Okay. The intersection of any set with a null set is a null set. And the union of any set with a null set is the original set. Now these last two statements are important, because notice that if the null set is kind of interpreted to be 0, it suggests that that intersections are like multiplications and unions are like additions. Okay. And in fact that is the case. And the reason why we need to know that fact is there's one thing we haven't discussed, which is what happens when we have intersections and unions in the same set operation. So now we come to our last important rule, which is that intersections take precedence over unions. Okay? Because multiplication takes precedence over addition, right? So intersections take precedence over union. So if I write this sort of statement here on the left hand side, it's not ambiguous. It means that first I take the intersection and then I take the union of that. Okay? Alright, disjoint's a very important fact. It's a very important term we use, and basically it says that for two sets to be disjoint, their intersections a null set. In other words, disjoint sets are sets that have nothing in common. They have no overlap. Alright, that's all we need to know for set theory. Now we're going to go ahead and apply this to probability theory in the next video.